In this particular lecture, we'll talk about matrix representation of an operator. But before that, there are a few things we can discuss. First of all, we already know that the eigenvalues of a Hermitian operator, which is that A is same as A of a joint, our eigenvalues are real. There is another piece of information about the Eigen Functions of a Hermitian operator, and which is, let's say if you have a state phi and A is being applied. As a matter of fact, let's calculate this quantity. Well, the two Eigen Functions, we are talking about Eigen Functions. Let's say there is a certain Eigen Function of this matrix A, and let's calculate this. Phi I and phi j. Let's calculate this quantity. Now, if you apply A on this side, we will get AI phi j phi I. But if you apply A on the other side, which means you can move it to the other side so that it starts looking like this. Then we know A adjoint is same as A, and we get AJ. This is not theta, and this is phi. And we subtract these two, we get 0 equals AI minus AJ phi j phi I. Now there are two things we can deduce. That means that AJ is same as AI, which means the two eigen functions are actually the same because they are have the same eigenvalues. The other thing that can be deduced is that phi j is equal to 0, which means they are orthogonal. So if AJ is not equal to AI, that means they are distinct, then they are orthogonal. Then the two eigenfunctions to which they correspond are orthogonal. Okay. And orthogonal eigenfunctions are important because we know, like in our Euclidean case, we have x, y, and z axes which are orthogonal to each other, and that makes life very easy. And any state can be expressed as a linear combination of these eigenfunctions, these basic states. So moving forward to matrix representation of an operator, let's say we have a collection of orthogonal eigenstate, eigenfunctions. Well, not eigenstate, eigenfunctions. And they are complete, which means they are good enough to satisfy, to express a certain state. They form a complete system. So any state psi can be written as a linear combination of AI. Now let's use a different notation because we have been using A for eigenvalues. Let's say BI phi I, something like that. So this is the idea. And then let's calculate, and there's one more thing that can be understood, is that because they are orthogonal, phi I, phi j is delta ij. And so let's calculate this particular quantity. Phi sum operator A, psi sum operator A, sum up, and then psi. The expectation value of the operator A on the eigenstate, on the state vector psi. Okay, and then we know we can write this as, we can express the whole thing as, first of all we can apply the unity operator because it's a complete set. We know that unity operator can be written as I Well, looks like I have run out of space, so let me write it someplace else. The unity operator is sum over I phi I phi I. This is unity operator, and we can put in unity operator in both these places. And if you do that, it's going to look like sum over I as well as j, because here unity operator will be summed over I, here unity operator will be summed over j, and that gives us phi j phi I, phi j a phi I. On the other side it's phi I. This should be star. Well, you know, this is how it's written. Phi I and then psi. If it's a continuous system, we know that it's written as phi star psi star a psi dx 0 and so on, whatever variable which define phi. Here we are talking about a discrete system with not infinite number of eigenfunctions, but well, it holds true for infinite number of functions also, but for the sake of practicality, let's say there are a finite number of eigenfunctions, so that our matrix is actually finite in size. So we see that this can be written like that. Now this is for a continuous system where this variable is changing continuously. Okay, for discrete system, here it is, and we will have problems in quantum mechanics that can be discrete system or can be continuous system. As a matter of fact, we can have discrete as well as continuous properties in the same eigenfunctions. Anyway, now if we look closely, this is the projection of psi on the phi jth eigenfunction, and this is the projection of psi on the phi ith eigenfunction. So in a way, this is a column matrix, column vector, and this is a row vector. Same as we know that if xi plus yj plus zk is a vector, x is the projection on on the x-axis, y is the projection on the y-axis, and z is the projection on the z-axis. And this is nothing but projection, because it's an inner product between the vector and the eigenfunction or the axis. So this can be written as this times this, or sorry, not like that, but like this, because we know that psi star is actually a row matrix, a row vector, and this is nothing but there are entries for different j's and I, because you see j changes from 1 to some value. So phi, so all these entries here correspond to phi j, a, phi I. So with different values of I and j, it fills the matrix. And here are the projections. These projections with I equals 0, it goes here, which is or 1. Let's start counting from 1. So phi 1. Like this, the last column, let's say there are n eigenfunctions, then it's going to be phi n psi. Similarly here, now in this case, it's going to be actually just the other way around. It's going to be psi and phi 1, and here it's going to be psi phi n, and here you know this is what is going to fill. Now as you can see, this is again a matrix problem, and these and A, and here what we have done, we have written A as a matrix representation. A is now as a matrix. It's operating on the row and column vectors. Now it's a matrix. It's written in the matrix form. So it's the matrix representation of an operator. which is in the basis function of these phi's, which is the basis of these phi's. So the basis functions or the eigenstates remain the same thing, are these phi j and phi I, and in this phi j and phi I, which is nothing but eigenfunctions of A itself, well, that's a wrong statement. A is being written in the basis of basis functions phi j and phi I, and this is the matrix representation. If you have a different basis function like some other basis function, then your matrix changes accordingly, and we'll see some examples.